Okay, next one is P14. Do not panic if you think there's no P13. You're lucky, you haven't got too much of this. So here's P14, and we've got a basic one that you do in maths loads. So let me just go back on that. You're going to need Dave's massive Veruca. Now, in physics, we use rho for density, so that can be replaced with that. And the crucial part is we know that the mass is in grams or kilograms, the volume will be in centimetres cubed or metres cubed, and the density will then be grams per centimetres cubed or kilograms per metres cubed. So just got to be careful that everything sings together. So a piece of metal has a mass of 6.4 grams. The density of the metal is 5.56 grams per centimetres cubed. Perfect. The grams and the grams are speaking to each other. What is the volume? So using Dave's massive Veruca, I've now got V equals the mass divided by the density. 6.4 divided by 5.56. I've got 1.15. And my unit for volume comes from the unit within the density. Next one, I'm not going to do too much on 14.2. You've done this in chemistry to death. Explain how the particles in solid gold are arranged and are moving differently to liquid gold. So I've got to say about the arrangement. So obviously in solids, they're in a fixed arrangement. In liquids, they're in a random arrangement. And then the moving, solid particles are vibrating around fixed positions. And in liquids, they're flowing over each other. So here we go. So in a solid, the particles are touching each other and are vibrating in rows around fixed positions. In a liquid, the particles are touching each other, so that's the same, and they're moving over each other randomly with small gaps between them. So I've just got this idea of the one, they're in fixed positions, the other one, they're random positions. They're touching in both, but the one, they're vibrating, and the other one, they're overlapping. I hope that makes sense. A lot of marks there. What is sublimation? So that's a change of state from solid to a gas, or straight from a gas to a solid. And then define specific heat capacity. I've definitely taught you this one. And we've said HE11, and then we're away. So it's the amount of heat energy for 1 kilogram of metal to increase in temperature by 1 degree C. What is the specific latent heat of fusion? So now we've got to know fusion. Well, this is solid to a liquid or liquid to a solid. So I could either pick melting or I could pick freezing, either of those words, but I've got to put that in because it's fusion. And again, we've got HE1 and then name the change of state. So it's the amount of heat energy, tick, for 1 kilogram to change from a solid to a liquid, or I could do from a liquid to a solid. Okay, next one, we've got a calculation. So we're going to need my quirky llama, which we've just learnt, and its specific latent heat of vaporization, so LV. What's the total thermal energy? Okay, so I need to work out Q for 40 grams. So I'm going to have to divide that by 1,000 because I can see the unit is in kilograms, and then I'll get it in joules. So Q equals ml. That's going to equal 0.04. I've got my unit change in there, times the number they gave me, 90,400, and the answer's joules. Next one, an immersion heater provides 1.8 kilojoules of thermal energy, so that's going to have to be changed, times 1,000, 1,800, to 1.2 kilograms. Yeah, we're happy with that. What's the specific heat capacity value for the metal block? And we're given Q equals MC delta T. So Q, MC delta T. So we want to work out C. And then we've just got to put all of the values in. We're going to get a mark for working out the energy difference. So delta T, 31, take away 21 is 18. And then we've got to rearrange it. So C equals Q divided by the mass times delta T. C equals the 1,800, pull that down from there, times 1.2 because it's in kilograms, happy days, times 18, the temperature change. That gives me a value of 83.33, done. But then for my unit, it's going to be, we've changed this to joules, joules per kilogram, degree C is the unit. And if we look at Y, C, I've got joules on the top. So just looking at that there, divided by kilograms, degree C. And then we just write it like that. Okay, really important one. So we've got a graph. Ice is removed. Use your graph. Explain the changes that take place in 20 minutes. That's giving you time. So you've got to state what's happening in each of the bits. So what's happening here, what's happening here, what's happening here, what's happening here. And I've got to tell the examiner where am I in terms of the time for each of these changes. And that's always the same on every single graph. Say whatever the time are, say what's going on. So here we go, we'll start with the first part. 0 to 1 minutes, the ice is heating up, and it's heated up, and we can see that there, it's heated up by 20 degrees C. You can see that there. And what I can know is I'm increasing the kinetic energy stores here. I've taught you a rise, kinetic energy stores, potential energy stores, kinetic energy stores, potential energy stores. Heat you up, change state, heat you up, change state. And then we can see, oh, I get this. I'm going to take my ice out and it's a solid. Here it's changing to a liquid. Here that liquid is heating up, and here we've got to go into a gas, and we can see, yeah, get it, 0 and 100 degrees C. And I'm going to mention those. Okay, next one. So between 1 to 7 minutes, the ice is melting, and it's at 0 degrees C, which is its melting point. The solid is changing to a liquid. I am increasing the potential energy stores. I'm breaking bonds between the solid. Done. Next one. Well, now I've got to go from 7 up to, is it 14 and a half, 14? Yeah, something like that. So next one, well, between 7 to 14, the water is heating up, and it's heated up by 100 degrees C. Now it's at its boiling point, or getting close to its boiling point of 100, so the kinetic energy stores are increasing. The liquid particles are moving faster. And then the last part, between 14 to 20 minutes, the water is boiling at 100 degrees C. This is its boiling point. A liquid is changing to its gas. The potential energy stores are increasing. I'm moving particles further away from each other. They're going off into the air. And then eventually particles will leave the beaker. So the mass will go down inside the beaker. And that's that done.